Network protocols form the fundamental language of digital communication, governing how devices connect, exchange information, and maintain security across networks of all sizes. These meticulously designed sets of rules and conventions serve as the invisible infrastructure supporting everything from simple web browsing to complex cloud computing architectures. At the most basic level, protocols like TCP/IP establish the essential framework for Internet communication, breaking data into packets, ensuring reliable delivery through sequence numbers and acknowledgements, and reassembling information at its destination. The Internet Protocol Suite, commonly known as TCP/IP, represents the foundational protocol stack that powers modern networking, consisting of 4 distinct layers: the link layer handling physical network connections, the Internet layer managing routing between devices, IP, the transport layer ensuring reliable data delivery, TCP/UDP, and the application layer encompassing protocols like HTTP and FTP that users directly interact with. Each protocol in this stack serves specific purposes while working in concert with others. ARP, Address Resolution Protocol, translates IP addresses to MAC addresses at the link layer, enabling devices on the same local network to find each other, while ICMP, Internet Control Message Protocol, provides vital network diagnostics through tools like ping and traceroute. At the transport layer, TCP, Transmission Control Protocol, offers connection-oriented communication with error checking and flow control, making it ideal for applications requiring reliable data delivery like web browsing or email, whereas UDP, User Datagram Protocol, provides lightweight, connectionless communication better suited for real-time applications like video streaming or VoIP, where occasional packet loss is preferable to latency. The application layer hosts some of the most recognizable protocols that define our daily Internet experience. HTTP, Hypertext Transfer Protocol, and its secure counterpart, HTTPS, form the backbone of web communication, while DNS, Domain Name System, acts as the Internet's phone book, translating human-readable domain names into machine-friendly IP addresses. Modern iterations like HTTP2 and HTTP3 have dramatically improved web performance through features like multiplexing and reduced latency, while DNS over HTTPS, DOH, and DNS over TLS, DOT, have enhanced privacy by encrypting traditionally plaintext DNS queries. Email communication relies on another set of application layer protocols, SMTP or Simple Mail Transfer Protocol for sending messages, POP3, which stands for Post Office Protocol, and IMAP or Internet Message Access Protocol for retrieving them. Each of these has distinct advantages in terms of server storage versus local message management. File transfer protocols like FTP or File Transfer Protocol, and its secure variants SFTP and FTPS, enable efficient data movement across networks. Meanwhile, SMB, or Server Message Block, and NFS, or Network File System, facilitate file sharing in local network environments. At the same time, protocols like DHCP, or Dynamic Host Configuration Protocol, automate network configuration by assigning IP addresses to devices. NTP, or Network Time Protocol, synchronizes clocks across systems, a surprisingly critical function for security protocols and distributed systems. The importance of these protocols extends beyond mere functionality. Their design decisions directly impact network security, performance, and reliability. Vulnerabilities in protocol implementations frequently lead to widespread security issues. Heartbleed, for instance, exploited a flaw in OpenSSL's implementation of the TLS protocol. DNS cache poisoning attacks take advantage of weaknesses in traditional DNS resolution. Security-specific protocols form another crucial category, implementing encryption authentication and secure communication channels across potentially hostile networks. SSL/TLS, which stands for Secure Sockets Layer and Transport Layer Security, provides the encryption backbone for secure web browsing, online banking, and virtually any application requiring confidential data transfer. It uses sophisticated handshake protocols to establish secure connections and certificate authorities to verify server identities. VPN protocols like IPsec, OpenVPN, and WireGuard create encrypted tunnels through untrusted networks. Meanwhile, authentication protocols like Radius or Remote Authentication Dial-in User Service and TACACS, plus which stands for Terminal Access Controller Access Control System, plus Managed Network Access Control. At the lower layers, security protocols like WPA3 protect Wi-Fi communications, replacing the flawed WEP and improving upon WPA2 with stronger encryption and protection against offline attacks. The evolution of these security protocols reflects an ongoing arms race between cybersecurity professionals and malicious actors. As vulnerabilities are discovered in older protocols, like the complete compromise of WEP or the partial weaknesses in WPA2, new standards emerge to address these flaws while maintaining backward compatibility where possible. Emerging protocols like QUIC, which stands for Quick UDP Internet Connections and forms the basis of HTTP/3, demonstrate how modern protocol design incorporates security from the ground up rather than as an afterthought, with encryption mandatory rather than optional. Similarly, DNS security extensions, or DNSSEC, add cryptographic verification to DNS responses, preventing cache poisoning and other DNS-based attacks that have plagued the Internet for decades. Industrial and specialized environments rely on their own sets of protocols tailored to specific requirements. Modbus and DNP3 dominate industrial control systems, while financial networks use protocols like SWIFT and FIX for high-value transactions. The Internet of Things, or IoT ecosystem, has spawned numerous lightweight protocols like MQTT, which stands for Message Queuing Telemetry Transport, and CoAP, or Constrained Application Protocol. These are designed for resource-constrained devices, often prioritizing efficiency over features. Real-time communication applications leverage protocols like RTP, the Real-Time Transport Protocol for media streaming, and WebRTC for browser-based video conferencing. Each of these solves unique challenges in timing, synchronization, and quality adaptation. Wireless technologies introduce another layer of protocol complexity. Bluetooth uses its own protocol stack for short-range communication, while cellular networks employ protocols like LTE and 5GNR, or New Radio, with their intricate handoff procedures and quality of service mechanisms. The proliferation of these specialized protocols creates both opportunities and challenges. While they enable optimized performance for specific use cases, they also expand the attack surface and require security professionals to maintain awareness of an ever-growing array of technologies. The development and standardization of network protocols follow formal processes through organizations like the Internet Engineering Task Force, which publishes protocol specifications as requests for comments, and the Institute of Electrical and Electronics Engineers, which oversees standards like Ethernet and Wi-Fi. These standards bodies ensure interoperability while allowing for gradual improvement. For instance, the transition from IPv4 to IPv6 has been ongoing for decades, with the newer protocol solving the IPv4 address exhaustion problem while introducing enhanced security features like mandatory IPsec support and improved address auto-configuration. Protocol development balances numerous competing concerns: backward compatibility versus innovation, security versus performance, simplicity versus feature richness, resulting in designs that often represent compromises between ideal solutions and practical constraints. The OSI, or Open Systems Interconnection model, while not directly implemented in real networks, remains a valuable conceptual framework for understanding protocol relationships and interactions, dividing network communication into 7 layers: physical, data link, network, transport session, presentation, and application, each with well-defined responsibilities and interfaces. Modern networks often blend protocols from different eras and standards, creating complex ecosystems where legacy systems must coexist with cutting-edge technologies. This reality frequently introduces security vulnerabilities when older, less secure protocols remain enabled for compatibility reasons. Troubleshooting network issues requires deep protocol knowledge, as problems can manifest at any layer, from physical cable issues at Layer 1 to misconfigured firewalls at Layer 4 or broken authentication at Layer 7. Protocol analyzers like Wireshark allow network professionals to inspect communication at the packet level, revealing the intricate dance of protocols that underlies even simple operations like loading a web page. Understanding protocol behavior is equally crucial for cybersecurity. Firewalls make decisions based on protocol headers, intrusion detection systems, analyze protocol payloads for malicious patterns, and advanced threats often exploit subtle protocol vulnerabilities or implementation flaws. The Log4j vulnerability of 2021, for instance, involved abuse of the JNDI, or Java Naming and Directory Interface Protocol, demonstrating how even obscure protocols can become attack vectors when improperly secured. Similarly, the Mirai botnet famously exploited default credentials in the Telnet protocol to compromise Internet of Things devices, while the Eternal Blue exploit took advantage of vulnerabilities in Microsoft's implementation of the SMB protocol. These incidents underscore why protocol knowledge remains essential for both network operations and security professionals. You can't secure what you don't understand. Looking ahead, network protocols continue evolving to meet new challenges. Quantum-resistant cryptographic protocols are in development to counter future quantum computing threats, while new congestion control algorithms aim to maintain performance on increasingly crowded networks. Protocols like multipath TCP enable devices to simultaneously use multiple network connections, improving reliability and performance, and blockchain-based protocols are exploring decentralized alternatives to traditional networking functions. The rise of edge computing and fifth-generation networks is driving innovation in protocols optimized for low latency and distributed architectures. And, ongoing work on named data networking proposes a fundamental shift from host-centric to data-centric internet architecture. As networks grow more complex and interconnected, the role of protocols in ensuring secure, efficient communication becomes ever more critical. They remain the unsung heroes of our connected world, quietly orchestrating the flawless exchange of information that modern society depends on. For technology professionals, deep protocol knowledge provides both a lens for understanding network behavior and a toolkit for solving problems. Whether it's optimizing performance troubleshooting issues or securing systems against ever-evolving threats, this knowledge is indispensable. In this context, network protocols represent not just technical specifications, but the very language of digital civilization. They are constantly evolving to meet new needs while maintaining the reliable foundation our interconnected world is built upon.